Welcome to EE331 Lesson 22, where we'll discuss AC Thevenin equivalent circuits. Yes, I know many of you were probably dreading this when you started seeing how AC would mirror DC, and we mentioned the words linear circuit in the last lesson. Recall that Thevenin's theorem states that any two-terminal linear circuit can be represented by an equivalent model. In DC, that was a voltage source, Vthevenin, in series with a resistor, Rthevenin. In AC, the result will be similar, but now I'll have a phasor voltage Vthevenin and a complex impedance Zthevenin instead of just an Rthevenin. The process for determining the Vthevenin and Zthevenin values are the same and require two sub-processes, just like in DC. For the first process, Vthevenin, you need to remove the load and then assess the voltage at the terminals VAB, which is where the load used to be, which is by definition Vthevenin when the terminals are open. For the second process, Zthevenin, you need to start over from the original circuit and remove the load, then turn the sources to zero. This means either a short or an open, depending on the type of source. Then you'll be able to assess the equivalent impedance between points A and B, which is the definition of Zthevenin, the Thevenin impedance. Let's practice this procedure on a simple example. I have an AC circuit here with ZL, my load. We can see that we're good to go to start working in the frequency domain since the source is already in phasor form and the impedance of the capacitor is shown. For Vthevenin, I need to remove the load, which means that I draw a circuit like so. You can see that Vthevenin is the voltage between the terminals A and B and is across the capacitor minus J40 ohms. The easiest way to solve for Vthevenin in this problem is to use the voltage divider rule. I can assess that Vthevenin, which is across the capacitor, is equal to the total voltage, 100 angle 0 degrees volts, times the fraction where I put minus J40 ohms at the top and 40 minus J40 ohms on the bottom. That obtains a Thevenin voltage of 70.7 angle minus 45 degrees volts. That's the value of this voltage source. For Zthevenin, I need to do two things in my drawing. I need to remove the load, and then I also need to turn the sources to zero. I have a voltage source, so that means I need to make it a short. We can see that Zthevenin here is the parallel combination of the 40 ohms and the minus J40 ohms because the short gets absorbed into node B. If I do that parallel combination correctly, I get the answer 20 minus J20 ohms. That's the value of Zthevenin. Now that we have a Thevenin equivalent circuit with Zthevenin, let's talk about how we could represent Zthevenin with components. Any Thevenin impedance Zthevenin can be represented by a maximum of two components, one resistor for the real part, and one inductor or one capacitor for the imaginary part. This will depend on the sign of the imaginary part of the impedance. Inductance is associated with positive imaginary impedance, and capacitors are associated with negative imaginary impedance. These impedances must be in series since the Thevenin equivalent circuit is always in series. What we're saying is that Zthevenin, which we've drawn as a block up at the top right, can be represented by real components, resistors, inductors, and capacitors. In the case of this problem, where Zthevenin is equal to 20 minus J20 ohms, this can be most simply represented by a resistor representing the 20 ohms and a capacitor representing the minus J20 ohms. In the Thevenin equivalent circuit, that means that we would draw a voltage source like so. This is a representation of the circuit that helps translate the numbers into physical components, even if they're just a model. This process can be helpful conceptually. As always, notice that for the follow-on problems with the Thevenin circuit, that they all become series circuits. That is, once Z load is attached, I have a simple series circuit where the most natural thing to do is to calculate the current in that circuit. In this practice problem, I'm going to obtain the Thevenin equivalent circuit for this AC circuit. I'm asked to find it between the terminals A and B, which you can notice are the same as E and C, so we don't really need to talk about E and C. I'm also instructed to depict the Thevenin equivalent circuit using R, L, or C symbols, and then to actually calculate the values of those components. I'm told the frequency of the system is 400 Hz. Although this circuit is drawn slightly unusually with the 45-degree angle components, we can draw an equivalent circuit that looks like this. Notice that between the two representations, all of the elements are connected to the same components at the same nodes, so the circuits are equivalent. We can also check that all of the components are in terms of phasors or impedances, and that's true, so we're good to go. Remember that the Thevenin voltage is the voltage between A and B. Note that the Thevenin voltage can also be expressed in terms of node voltages as the difference between VA and VB. This is probably the best way to approach this problem because it leads us to a rather simple solution. Notice that the minus J6 and the 8 ohms are in series. Notice also that the 4 ohms and the J12 ohms are also in series. If I take the ground node to be the minus terminal of this voltage source, then VA is like so across the 8 ohms, and VB is like so across the J12 ohms. Lastly, observe that the voltage source is between the two nodes D and F, which is across both series sets. Therefore, I'm set up for a voltage divider in both cases. For VA, I solve by the voltage divider that VA is equal to the total voltage, 120 angle 75 degrees volts, times the fraction where 8 ohms is on top and 8 minus J6 ohms is on the bottom. The 4 ohms and the J12 ohms are not included because they're not part of this series set. If I calculate that correctly, then I'm going to get that VA is equal to 96 angle 111.87 degrees volts. I can solve for VB by a similar procedure with the voltage divider rule. That is, VB equals 120 angle 75 degrees volts times the fraction, where on top I have the J12 ohms, and on the bottom I have the 4 plus J12 ohms. Doing that obtains that VB is equal to 113.84 angle 93.435 degrees volts. Lastly, for my solution, that Thevenin equals VA minus VB, I take the difference between those two terms and obtain 37.95 angle minus 139.7 degrees volts. I start over with a new process for Thevenin, where I remove the load and kill the sources. In this case, I have a voltage source, so I kill it as a short. Remember that Thevenin is by definition the equivalent impedance between the points A and B. That means that you should imagine yourself as a charge who lives at A and who has an objective to get to B. You can't jump the gap, so you have to find all the possible routes from A to B through the impedance elements. A good practice in a problem like this is to acknowledge that the short will connect two nodes, and we should give names to these nodes to help them. We can see that originally we labeled a D and an F, but if we notice that the short connects them, they're really just one point now. The drawing is kind of confusing, so let's use a navigation map. If I start at A, then I can see that I'm touching at A the 8 ohms and a minus J6 ohm. If I get through the minus J6 ohm, I arrive at D, which we know is at the same point as F. We can see that 8 ohms is connected to that exact same point because D is the same as F. So they're connected like so. Once I get to D, we ask who else is touching D except for the minus J6 and the 8 ohms, and we can see that we're touching the 4 ohms up here, and we're also touching the J12, again because D and F are the same point due to the short. Now we can ask where do we arrive after going through the 4 ohms and up through the J12 ohms, and we arrive at B, which is our final destination. Now it's very apparent to see that the equivalent impedance between A and B is equal to 8 ohms in parallel with the minus J6 ohms plus the 4 ohms in parallel with the J12 ohms. If you do that correctly, you'll find that Thevenin is equal to 6.48 minus J 2.64 ohms. When putting together our sketch of the Thevenin equivalent circuit, we can do so with the voltage source that has the value we calculated, 37.95 angle minus 139.7 degrees volts. We could represent Thevenin as a block, but they specifically asked us to use R, L, or C symbols. We can see that the Thevenin impedance has a real part and it has an imaginary part. The real part we can represent with a resistor. In the imaginary part, we need to look at the sign. Since it's a negative J, we know that it's capacitive, and we can draw a capacitor like so. I can associate the 6.48 ohms with the resistor and the minus J 2.64 ohms with the capacitor. That'll sit between A and B in series with the voltage source. Lastly, they wanted us to actually calculate the values of resistances, inductances, or capacitances if the frequency is 400 Hz. The resistor's impedance is not related to the frequency. Only the capacitor's impedance is related to the frequency. Remember that ZC equals negative J divided by 2 pi f C. I know ZC in this case, so I can solve for C. That is, C equals negative J divided by 2 pi f ZC. With some numbers, that's the minus J divided by 2 pi 400 times the negative J 2.64 ohms. We can see the negative J's will cancel, and if we solve, we obtain a capacitance of 150.7 microfarads. In this practice problem, I'm again going to get the AC Thevenin equivalent circuit at the terminals A and B. This is where we'll eventually place a Z load. I then am going to be asked follow-on questions about the current through that load and the voltage across that load for various different values of the load. First, let's get the Thevenin equivalent circuit. The circuit already is missing Z load, so I'm already set up to solve for V Thevenin, which had the step of removing the load and then assessing the voltage between A and B. Again, remember that V Thevenin can be written in the nodal format as VA minus VB. To help us with the node voltage notation, let's assign a ground to the negative terminal of the voltage source. Doing so sets this entire bottom node to 0 volts. We can intuitively see that there's going to be no current jumping the gap between A and B, that is, the current equals 0. Since the 10 ohms is in series with the open, we know that the current through the 10 ohms is also 0. We can also assess then that the voltage dropped across the 10 ohms is 0 volts. Therefore, we can say 0 plus 0 volts gets us a node voltage at B of 0 volts. This means that we can simplify our expression for V Thevenin and just say that it's equal to VA. It also means that the effective circuit, when solving for V Thevenin, does not include the 10 ohm resistor at all, because the 10 ohm resistor does not carry any current. That is, I can solve for VA with this series circuit. This is a perfect setup for the voltage divider approach again, and I use the voltage divider rule, which tells me that VA equals the total voltage across the series set times a fraction, and on the top I put the minus J 4 ohms, because that's what VA is across, and on the bottom I put the series combination, which is 6 plus J2 minus J4. If I do that correctly, I'll get that VA is equal to 63.246 angle minus 51.57 degrees volts. Since V Thevenin is equal to VA, I can say that's equal to V Thevenin as well. Now let's solve for Z Thevenin. For Z Thevenin, I need to kill the sources and remove the load. The load is already removed, so kill the source means replacing that voltage source with a short. Notice here that I include the 10 ohms, even though it did not matter for my calculation of VA in the last step. The 10 ohms will matter for the Thevenin impedance, because it's in the pathway from A to B. Again, V Thevenin and Z Thevenin are separate processes. If it isn't readily apparent to you, use a navigation map to calculate the equivalent impedance between A and B. We see that at A, we are touching a J2 and a minus J4 ohm. After going to the J2, I'm at some other node, I'll call it C, and I'm touching a 6 ohm. After going to the 6 ohm, I'm at this bottom node. Let's give it a name and call it D. Notice that D spans all the way through the short and includes the bottom node and up to the left side of the 6 ohm. That means that it's touching minus J4 as well, so we'll connect them. And then from D, the only item that's touching that we haven't accounted for is the 10 ohm. After going through the 10 ohm, we arrive at B. Therefore, I can say that Z Thevenin is equal to 10 ohms plus the parallel combination of minus J4 ohms and the series set of J2 ohms plus 6 ohms. If I do that correctly, I'll find that Z Thevenin is equal to 12.4 minus J 3.2 ohms. We can draw the total Thevenin equivalent circuit like so. Notice that I've used a capacitor representation for the imaginary part of the Thevenin impedance, because it's a minus J. For the follow-on parts of the question, I'm asked to solve for the current through and the voltage across a load for various different values of that load. We should use the Thevenin equivalent circuit when we solve for any of these follow-on questions. Note that the current is particularly easy to solve for because this current, I load, is in fact the only current in the circuit because it's a series circuit. Generically, I can solve that I load is equal to the total voltage, which is Vthevenin, divided by the total impedance, which is Zthevenin plus Zload. Vthevenin and Zthevenin will be fixed, but Zload will have different values. To solve for the voltage across the load, Vload, you could either choose Iload times Zload, or you could use a voltage divider approach, where Vload equals Vthevenin times Zload divided by Zthevenin plus Zload. Both approaches are equivalent. You can easily substitute the values in for Zload, and we've already calculated Vthevenin and Zthevenin, so we won't walk through the calculations for these. You should obtain numbers like so. One thing you might notice here is that with these complex load values, we don't really get an intuitive understanding of what's going on as we change the load values. We can see that the load current's magnitude changes, but it doesn't seem to do so in some kind of consistent way, and the phase is changing as well. The same can be said for the voltage. If we want to assess what's going on, particularly with power, we need some other tools. We mentioned this idea of power because Thevenin is usually used to talk about the maximum power transfer conditions. Note that the maximum power transfer conditions are not the same in AC as they are in DC. Specifically, in AC, we need Zload to equal Zthevenin conjugate. Remember that this star, the conjugate operator, means that we mirror the complex number across the real axis. That is, we flip the sign of the angle, or we flip the sign of the imaginary component. The reasons for doing this are not going to be obvious until we really delve into AC power. AC power is complex, and we'll probably need a couple lessons to discuss it fully. However, if we use our Thevenin equivalent circuit representation with components, we can actually see what's going on with the Zload and Zthevenin conjugate. Take, for example, I have a Thevenin equivalent circuit. It has a voltage Vthevenin and a Thevenin impedance that is equal to some Zthevenin. Since that can generically be complex, you could imagine that to be a resistor and some inductive value. We'll call that R Thevenin and plus J X Thevenin, where X is the reactance part of the Thevenin impedance. Now let's set Zload equal to Zthevenin conjugate. That means that Zload will be equal to R Thevenin minus JX Thevenin. That's because the regular Zthevenin was R Thevenin plus JX Thevenin. We flipped the sign of the imaginary component. Let's draw that in the circuit. If we do so, the resistor is the same, and the minus JX Thevenin is capacitive. In this series representation of the circuit, we can now see that the R Thevenin values are equal, but there's a plus JX Thevenin and a minus JX Thevenin. They're going to cancel each other when we add up these series impedances. That is, we can see that Z total will equal R Thevenin plus JX Thevenin plus R Thevenin minus JX Thevenin. The result is entirely real, and we all have no imaginary component. Maximum power transfer occurs when we cancel all the imaginary impedances and we match the real impedances. These are the two conditions required for max power transfer. Let's revisit the numerical answers to this practice problem to talk about this idea of maximum power transfer. If we're really going to analyze what's going on conceptually, let's consider that the power as a function of time, or the instantaneous power, P of t, is going to be equal to the voltage as a function of time times the current as a function of time, where the voltage is in volts and the current is in amps. And I'll get a power in watts. This has to be true since that's the way the units work out. If I were to convert Iload and Vload into time domain waveforms and multiply them together, I would get P of t, the instantaneous power. Before we go and take a look at some plots to see what happens for each of these three different conditions, note that these three conditions are specially selected. In the first part, we have just really matched only the resistance with the 12.4 ohms and not paid any attention to the imaginary part. In the second load, we've set that exactly equal to Zthevenin, but we did not apply the conjugate. In the third load, we're applying Zthevenin conjugate, so we expect the third load to actually absorb the most power. Let's go take a look at some graphs. For the Thevenin equivalent circuit that we're talking about, remember that Zthevenin is 12.4 minus J3.2 ohms. Let's consider what the graphs look like if I set Zload equal to just the real part, 12.4 ohms. If I do that, I get plots like this. Here we can see V load of t, that's the voltage across the load as a function of time, and I load of t, that's the current through the load as a function of time. If I were to multiply those two waveforms together, I would get P load of t, that's the instantaneous power absorbed by that load as a function of time. You can see that it goes up and down and up and down, so what really matters here over a cycle is to calculate what the average is. If I were to do that, which is plotted for us already, we would see that it's 39.68 watts, so that's our average power. Now let's consider what happens in the second case if I set Z load equal to the Thevenin impedance. That is, Z load equals 12.4 minus J3.2 ohms. We can plot those voltages and currents like so, which we already calculated, and again we see V load of t and I load of t, which are different values than before. Multiplying them together, we get the power as a function of time. Again, it's going up and down, and we can track its average, and this time we can see that the average is actually lower. It's 37.82 watts. Lastly, let's see what happens when we set Z load equal to the Thevenin impedance conjugated, that is, Z load equals 12.4 plus J3.2. We expect this to be the maximum power. The plotted curves look like this. Again, we see the voltage across the load as a function of time, the current through that load as a function of time, which are again different values, and multiplying them together get the power as a function of time. Tracking that average, we see that it's the maximum that we've seen so far, 40.33 watts. In fact, this is the theoretical maximum for any choice of load value. Bottom line, maximum power transfer to the load occurs when that load equals Z Thevenin conjugate.